Something useful. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day, and I just pray to help us to use this time wisely, Lord, to understand abstract algebra a little bit better, Lord. In your name I pray. Amen. So let me just begin by mentioning a few dictionary. So I've been reading the text, and I noticed his notation is not quite mine. So you guys have probably been reading some too. So I called it, well, let's see, let's start. First of all, I say that, I said something like S is acted on by G. Now, he typically would have said, he might also say that, but he would also tend to say that X is a G set, right? So his X is usually what I was using S for, which is slightly unfortunate. See, because I talked about the orbit, well, this is not unfortunate, orbit of X, that's fine, right? Orbit of X. What's his notation for orbit of X? In the textbook, he uses G dot X, which is not a bad notation for the orbit of X. It's everything that happens to X under G. Makes sense. Now here's where it gets a little unfortunate. I use G sub X for the stabilizer, right? Stabilizer of X. And in the textbook, he uses S of X for the stabilizer. So that's unfortunate because this use of S is in no way connected to this use of S. I use S for set. He uses big X for set, and that's fine. And then the other thing that's a little bit different was, what was my notation for fixed? I can't remember what my notation was for fixed subset. Was it, I can't even remember, was it S sub G or? S super G. So this he has as X sub F. So I guess if we were to use S, it would be, in the book's notation, it would be S sub F for fixed. So anyway, there is a, the notation's a little bit different, but it should be simple enough to translate. And the only theorem that, well, I'll say more about it tomorrow, but the other thing I would just say, since you're here, is that the thing I was confused about at the end of class, there's no need to be confused. It goes back to the difference between motion and symmetry. So symmetries are what? These are elements of the isometry group of, R3, for example, Rn. But let's say R3, just talk about a solid object for a second here. So isometries of R3 include both rotations and reflections, right? So they were right. If we look at the cube, and if we look at the faces on the cube as the set under which the isometry group is acting, and particularly the symmetries. So the symmetries, and I said it in class yesterday, but it's also right, but the symmetries of the cube, this is going to be a subgroup of the isometry group in R3. And so these are the isometries which fix the cube. So basically, sigma is an element of the symmetry group of the cube if sigma of the cube is equal to the cube again. So the sigma could either be rotations or reflections. The thing that was blowing my mind is I couldn't envision the reflections. So like, let's see here. So it's obvious to me that that front green face is fixed by the rotations, right? But what was not obvious to me was that there was another isometry that fixes the cube. The other isometry is it's the reflection over the plane z equals 0. If I put z equals 0 in the center of the cube. No, that's not it. That's not the right way to say it. Say this is the front side, right? Well, let's suppose that this green face it's like green on the front side and it's black on the back side, if you can imagine that, you know? There is a isometry which takes this to so that the black side is out after the isometry X. So that's, in other words, it flips the front face over, but it leaves all the other faces. It might flip other faces of the cube as well, but it leaves all of the other faces in place. So it's an isometry. It still fixes the cube, and oh, actually, I don't need that. I'm sorry, I'm an idiot. The other faces don't have to stay in place. They just have to. The question is, does the front face stay in place? It actually doesn't matter. The other faces can move around. That's fine. The question is which isometries fix the front face. So it's the rotations, the 4 rotations, but also there's also 4 reflections which fix the front face. But they turn the face inside out. So the thing I was trying to visualize that in terms of rotating a cube, which is crazy. You can't see the reflections of the cube in terms of rotations of the cube. This is what he talks about back in chapter 2 when he makes a distinction between motions and symmetries. So I was trying to count motions, of which there are 24. There are 24 motions. There are 24 actual physical motions that you can do to a cube, which will take the cube to the cube again with the same position in space. There's 24 different ways you can mess with a cube and get back to the cube again at that same point in space. But there are 48 isometries, but those would amount to turning the cube inside out, which you can't do. Now, so like the same is true if we look at like the symmetry group of a triangle, something like this, in the plane. If I'm trying to make it equilateral, right? There's obviously, you've got like the rotation by 60 degrees, you've got the rotation by I can't do math, 120 degrees, you've got, right? Is that right? If I take this and I rotate it up to here, if that's my rotation by 120 degrees, you can see that rotation, then the 240, right? And then, so if I call this thing R, because it's get tired of writing that, R squared, and you get back to the identity, right? This is a group. This is the group of motions on the equilateral triangle, as he calls them, motions. If I could, if I had a piece of paper and I cut out an equilateral triangle, I can move the triangle back to the triangle again, not distinguishing the corners with those motions, right? But there's additional isometries, right? Because you can also think about like doing that, right? If you flip that over, then that's also an isometry. It maps the triangle to the triangle, but you can't accomplish that in the plane, right? You have to flip the triangle out of the plane to do that. That's the analog, two-dimensional analog, which you can actually visualize of this, which is turning the cube inside out. But that's a four-dimensional process. Like if you could actually visualize that, that would require another dimension. But we can see the other dimension here, right? The isometry, the reflection here. You can actually visualize the triangle flipping out of the plane and back on again. And that's why the isometry group of an equilateral triangle is exactly D3. It's the 3 rotations, it's the 3 reflections, right? It's this one, there's also this reflection, and there's also that reflection, right? So 3 reflections, which are B, BA, and BA squared in our usual presentation of the dihedral group on 3, D3. And that's why we call it dihedral, because to understand it and understand it in terms of symmetry groups, you have to think about 2 faces. That's the dihedral's face, so it's 2-faced. It's really the group of motions for a 2-faced triangle. So something like that. So I thought these words might be helpful because I think I was a little bit unclear about what I was saying at the end of last class, and it could have used some. These smart creatures in here, they talk me out of things sometimes. Like, and my notes were wrong. I said that the isometry group of the cube has 24 things. That's just not the case. It has 48. Now you guys got questions, so I got that out of my system. You guys can ask away. I actually was worried I hadn't covered enough of the section. It was gonna mess our schedule up, but after I look at the section again, I think, you know what? I actually did cover the major parts of this section. I just he's got a few applications of the orbit stabilizer to various group. He's got a couple theorems about p groups at the end of the section that I haven't said yet. I'll probably project those the next class. I won't prove the CELO theorems. I'll just state them and show you how they work. That is my intention. Anyway, so you guys got questions? Or we can go home. Should put me to work. So the silent lecture, what we mostly learned was that let's just to recap it, what did we learn? If we want alpha to be a homomorphism from G to H, what was our main sort of observation that was thing that we were able to use to really chase down possibilities? What was it? I think it was just so the order, if the order of G must divide the order, wait a minute, is that right? No. I always get this backwards, you guys gotta watch me. The order of alpha of G has to divide the order of G, right? Assuming that we're in the finite context, I suppose. So like if you're starting, if you have an element, if your order G has order 7, if you have an element G with order 7, then you have to be able to assign it to what? I mean, that implies that the order of its image has to be what? You got 2 choices, right? 1 or 7. And then the other guiding principle is that if we have our group, if we have a presentation of the group in terms of generators and relations, then it suffices to map generators to map the generators. Once you map a generator, or once you map both generators, then you've completely fixed the action of the homomorphism on the group. That was a theorem that we didn't prove, but I stated at some point. But I probably should have proved it. Oh well. I think that was the main thing. And then, I mean, there's more, there's greedier things like what other properties are preserved by homomorphisms? Inverses, that's also true, but I was thinking more like if it's surjective, right? If G is abelian, H has to be abelian. If G is cyclic, H has to be cyclic, right? If G is non-abelian and it's a surjection, then H must also be non-abelian, right? I mean, there's these. We can look at structure as it has to be preserved onto the image, And conversely, the first isomorphism theorem in that discussion told us that the kernel of a homomorphism has to be normal, right? So if you write down a homomorphism, right, and you're looking, if your group is simple, meaning that it has no normal subgroups, but what, itself and the identity, then, you know, what kind of homomorphism can you write from such a group? Think about that. If G is simple, what are the possible homomorphisms? So you have alpha from G to H. What kind of homomorphism? I mean, what are your choices? You either have kernel of alpha equals to G itself, or you have the kernel of alpha is what? Yeah. If you're looking at a homomorphism from a simple group, you're either having one that's just the trivial morphism, right, that maps everything to the identity, or you necessarily must have a what? One-to-one, right. So for example, if you were looking for, say, what's a good example of a simple group? Basically, it means it has no normal subgroups to speak of. Wasn't S3 such a thing? I think. So if you look at this, right, and you want that to map to, I don't know, trying to think of something to put over there that's interesting, but then is impossible because of this. Suppose you want a non-trivial homomorphism from S3 to I don't know, Z12. Maybe this is too stupid, but I mean, I guess you could pick at the non-abelian aspect of it, but certainly, so if it's non-trivial, right, that would mean that the kernel of alpha is equal to 1, right? But then we're talking about a map it's a map on a finite set. So if we know that it's 1-to-1, we know also what, that, what's that? Yeah, the orders are different, right? I'm thinking, but I guess this implies that the image of S3 is what? And why do we call one-to-one maps one-to-one? Because they take one thing to one thing, right? So, right. So it's got 6 things in it, right? So I guess to make this more fun, you could have done something like, I don't know. I guess you could have done Z5. Right, then that would be impossible because you don't have 5 things to map. You don't have 6 things to map to. Anyway, I'm not sure my example is very interesting, but this is another tool in our toolkit. For simple group, you can think about like what are possible normal subgroups, because those are the only subgroups which can appear as kernels. This is sometimes useful. I don't think my example is very good. Sorry about that. All right, by now you guys have a question. I'm buying time for you. All right, 8.2 number 7, you say. All right. This is the training exercise? All right. Aha. If H and K are conjugate subgroups in G, show that the normalizer of H and the normalizer of K are likewise conjugate. So let's see here. H and K conjugate implies the normalizer of H and the normalizer of K conjugate. Assist, thank you. Let's see here. I think that one doesn't count against me because, you know. All right. So what does it mean for them to be conjugate? What are conjugate subgroups? There's different ways of looking at it. One way you can look at it, there exists an inner automorphism, which maps one to the other, right? But in particular, it means that there exists G in G such that G, H, G inverse is equal to K. So this is what it means for subgroups to be conjugate. One of the exercises I proved or indicated we should prove back in the day was that if you're given a subgroup H, right, and you conjugate it, you know, as a set, then that produces a subgroup. So that was one of our baby subgroup test examples. All right, so we would like to show that these two things are conjugate, right? So what is, we should probably, so let's try to think about this. Consider, what's n of H? It's the, what is this? Ooh, I should probably not use G. Let me use X and G. Mm-hmm. Yeah. Very good. And likewise, the normalizer of K would be, let's say, I'll use Y. I could use X again, it wouldn't matter, but Y and G such that Y, K, Y inverse is equal to K again. So, it's probably a smart way to do this. I'm not sure if my way I'm thinking about right now is that smart. Yeah. If I was a calculus student, I'd try to find a way to apply Cauchy's theorem to do this, right? It's a problem in this section. You have to use the methods of this section, right? No, I don't think so. I think this is just from the, it's probably just from the definition. That's what I was going to try. Do you have an idea? Oh, you think that, you think they're, do you think they're related by the same conjugate? That would be my hope. I mean, that would be the nicest thing, right? I mean, it could be that they're conjugate with respect to other elements, but we should try that. That would seem like the pick. Let's let X be an element of the normalizer of H, right? Oh, I'm sorry, that's not what I want. Let X be an element. I'm going to run out of letters here. Let A be an element of G, normalizer of H, G inverse. We're hoping that that's in the normalizer of K, right? It's possible that all that core technology that we had in the other problems would be useful here, but I don't have that internalized just yet. I worked out the problem, but it's not stuck in my head yet. I need to think more about that core stuff, you know. Okay, so, but that means what? That that means that A is equal to Gx, right? Gx, G inverse. For some what? Right. So then what does that give me? I mean, I'm trying to show that A is an element of n of k, right? Yeah, at this point, x is fixed. So if you want me, I could put, I mean, here it becomes, I mean, here. This is a specific one, right?
Wait, what were we trying to show again? A is in
We'd like,
K?
yeah, we'd like to show that A is in n of k, right? Because our suspicion, and this could be wrong, I mean, it doesn't, they could be conjugate by other things, right? But our hunch was that this was equal to this. So what does it take to show that A is in the normalizer of K? Yeah, so we should let Z perhaps be an element of what? A, K, A inverse? To test if A is actually in the normalizer of K, I need to do what? I need to check that A, K, A inverse is actually equal to K again. Now, there might be a way to, I mean, I follow elements because it just keeps me out of trouble, but it might be possible to do this without getting down into the, level of elements. I mean, we could just, before I commit to this, let's just consider, let me just try this, see if we can get away with not looking at elements. Consider A, K, A inverse. What's that equal to? A is that's G, X naught, G inverse, right? What's that?
Oh, never mind.
G is the that's fixed from this up there from the get-go. K, G, X naught, G inverse. But if you don't mind, I'm going to go ahead and sock shoes. So when I do inverse on A, what do I get? I get G, X naught, inverse, G inverse, right? But you notice that we have that H is equal to what? Right. So what's this? That's H. And we could rewrite that as Gx not inverse. I don't know if that helps or not, but
So isn't that just an element in GH and an element in G inverse? So that would have to equal K. From like the first.
oh, maybe I should, this is a bad move. It doesn't allow me to use the data, right? I should leave x naught to do its magic, because x naught is very special. Where is x naught from? Normalizer of h, which means what is x naught? How does x naught interface with h? Right. I think if we remember the definition of normalizer, so I mean, what does it mean? X naught's in the normalizer of h. What's that mean? That means that x naught h x naught inverse is equal to h again, because x naught's in the normalizer of h. So this is equal to g inverse, which, by the way, is k.
Could you not start from the very top where you say for all g and g, or there exists g and g such that g inverse is equal to k? And then could you not say that?
I'm not worried. I'm not with you yet. Where are you?
Up at the second line there. Start right there. And because you have that relation, could you not then say that for some x in a normalizer, that h is equal to x inverse, sorry, I can't talk, x inverse, and then say that for some y in the normalizer of k is equal to y times k to the y inverse, and so then you get to your second to last line, or third to last line in one step, I feel like.
I don't want to rule it out, but I need to see it written carefully.
Do you want me to write it up and show you after the class?
You can write now if you want. I will get you a workable marker.
I just want to know if this is something that you're allowed to do or not.
Here you go. This one works. It's right over here. There you go.
That's something you're allowed to do. You're only allowed to do it back at quick telling.
Right. Because you're starting with.
It's just, it is impossible to understand an equation verbalized. Like, it's just not.
Yeah. Because you're starting with this, right?
Right? That's given. There exists G.
Yeah. So, but for x in the normalizer of h.
Yeah, let's see this side. How it starts.
H is equal to x.
Right.
So you can sort of, those are the same thing. Can't you just say then g x h inverse. Because it's still the same set, right? And then for the k, you're also doing a substitution there, so that's y. But overall, that's still. Are you just allowed to do those substitutions, or do you have
So you're trying to show that. So for.
I just feel like
That's for that's
looking
true.
into this
So
step
that's of course true for any x.
in the normalizer. Regardless of which normalizer element it
Well,
is. I just feel like if you have an
right.
equivalence here, and you have h and k here,
I'm not saying you're wrong. It just takes me. I'm slow. G. So your point is h is actually equal to x inverse for any x in the normalizer of h.
right.
And you're trying to prove that G normalizer.
Because our final result is normalizer of H, G inverse is.
I mean, that's what you need to show, for sure.
But I mean, you just go straight from here to basically this step, just substituting in here. For some x in the normalizer, H is just equal to that, because that's what the normalizer does. I just feel like you can just jump straight to that. Is that not?
Yeah, you're fine. All right, let me think about this. So that's equal to k because it's given that GH, G inverse is k.
Right.
And then it's also k is equal to yk, y inverse. Well, I mean, I need a string of things I can agree with, like, so n of h, that, right, is, see, but why am I looking at that? Because I'm trying to show that that's equal to n of k. So your point is that that's equal to, just for any, well, I called it x naught, right?
Yeah.
So x naught, h x naught inverse, g inverse.
Which, because x is in the normalizer, that's just equal to GH, G inverse, which is k.
So that's equal to g h g inverse, which then is equal to k.
But k is equal to, oh, I see what you're saying. Yeah, I don't know if you can. Yeah, k is equal to yk, y inverse if y is in k.
Normalizer of k.
If y is in the normalizer.
If y is in the normalizer, okay, yeah.
I mean, I'm not saying I disagree with all the steps you wrote out. I'm just saying I don't necessarily see why you need to write all the steps out. If you can is that just generally to be more careful?
Well, I mean, you want an argument that people can read line by line and understand, right? Well, I'm not so quick to judge. I keep forgetting what I'm trying to do. It's my bad. So I'm trying to show that's equal to n of k.
Yes.
But k is definitely not equal to n of k, right?
Okay. Yeah, I see the problem with what I said.
I mean, that's a subset of n of k, I think. I think it's always the case that any subgroup is in its normalizer, right? Remember we said that if you look at the subgroup, how's it go? This is the normalizer of H is here, the group is up here, and what else was there? I'm trying to remember. I think that was it, pretty much. But the normalizer is the largest supergroup to H in which H is normal. So if H is a normal subgroup of G, the normalizer is G itself. Is there some other step in my argument which is missing from yours, Tim? Like, I mean, we both say that there exists a G such that H and K are conjugate. I also pick something in the normalizer, right? But it's,
I feel like I didn't show, I didn't show that K is equal to
A,
A inverse.
right. That's what's needed to show that A is actually in. Now, all my argument does not show that. You notice that my argument does not show that those are equal either. At the moment, my argument just shows that G normalizer of H, G inverse is a subset of N of K, right? This whole argument just shows that because this means that A is indeed an element of N of K, right? So we picked A in here, we showed it's in there, so that's a subset. That's a subset of that. And then the converse direction, we'd pick something in the normalizer of K, and I'm guessing through almost the same argument we can show the reverse inclusion. I mean, it's just some sort of flippity-floppiting of G and G inverse, but
You
yeah.
have to switch the G inverse and the G when you do the other one.
I know we can go through it. Let's see here. So, in that regard, your argument's not bad because you also show that G inverse. I think you also have that G eta of N of H, G inverse is a subset of N of K, which is actually all I have.
I guess what I was just doing was picking a random element of K and showing that it's basically equivalent through the first thing that you said.
Hmm. Okay, so this time we should pick, let's say B, an element of N of K, right? And I want to show that it's where? I want to show that it's in, my goal is to show it's in G, N of H, G inverse, right? What do I have to work with?
But does that need to be backwards? Like, does that have to be G inverse N of H, G?
I mean, I'm trying to show equality of these sets, so I better not do that.
Oh, yeah.
So, let's see here. Since that means what? That means that, yeah, hence, what's that mean? That means B, K, B inverse equals to K, right? But K is equal to, right? This is assuming we assume this. I mean, that was our way back here. My solution seems longer than it is because I took, I paused to write the definitions of things, and if you boil it down, it's not that long, my solution. Which isn't to say that there doesn't exist a more clever solution, by no means. Then what? Huh. What are we trying to show now? We would like to show B is in the normal, B is in that set. Huh. It'd be funny if I've just done the easy direction, and this is actually the hard one, right? Yeah. Get rid of the G's. So we've got G inverse B, K, B inverse G equals to H. And then that K can be rewritten as H by G inverse B. I'm not sure this helps or not. I'm just going to try something. G, H, G inverse B inverse G. Yeah, try something. Let's see here. And then does that help? I don't know if it helps or not.
Because it's conjugating by something. Isn't all that G?
Oh, that would say that that implies that G inverse BG, right, is an element of the normalizer of H, I think.
Yeah, which is what you need, because then you multiply the G's back over.
Does that do it?
Yeah, because you need to show B is an element of G and H G inverse, right?
Oh. B is an element of G and of H. Which is, which is what I wanted to show. Yeah, cool. Yay, just like I planned.
Wait, where did that come from? Oh, in the little element.
Yeah.
Oh, okay.
So if Yep. So fun with cosets. Keep in mind that I might ask you something simpler on the test, like, for example, HA equals to HB if and only if what? Right, so that is actually something you want to be able to prove carefully, right? And we did that. I went through it slowly and methodically. I mean, I know we're kind of being a little bit freewheeling and carefree at the moment with our coset manipulation, but don't forget, we have proved these things from the base up. Yeah. We just don't maintain that level of detail because that would destroy the whole purpose, which is abstracting. Yeah. Anyway, yeah, well, that's kind of an interesting problem. Any other questions? So I guess we can do one problem per meeting now. you guys have any other questions about like the isomorphism problems? Anything stand out there? Back in 210?
Section 10.
Yeah. Well, I guess we'll call it a day. So, thanks, guys.